Superconducting circuits can have resonant elements that are tunable, sometimes tunable by a direct current bias, meaning you inject a DC current into your circuit to change the resonant frequency driven by the alternating current. Pictured, you see multiple of these bias tunable devices multiplexed onto the same transmission line. Each of these resonating elements have a resonant frequency determined by this equation, where the inductance part, the L sub R, is tunable via a DC current. These resonating elements are coupled inductively to a transmission line, which acts as the highway for not only the microwave signal, but also the bias current used for tuning the resonant frequency. The main parts of these resonating elements are the large interdigitated capacitor, as well as the meandering inductor. This meandering inductor couples our element to the main transmission line, as well as provides a pathway to the tunable inductive element, the L sub R. This line you see right here. Current is forced to run through this wire, increasing the inductance of this wire, which in turn changes the resonant frequency of that element. Each of these elements had a unique resonating base frequency determined by its capacitance and inductance. The individual elements of the circuit are small, with it being micrometer features. The resonant frequency of each element is tunable. By adding current, you can shift the frequency down. For this material, the order of the current was on microamps, with a relatively small shift in resonance frequency. At best, the bandwidth shifted approximately 0.5% of the resonant frequency, but again for very low currents. This can be desirable, as these are done in cryogenic environments, and the more current you put into a cryogenic environment, the less cryogenic it becomes.